So greetings. In this short video, I'll review the Cramer's rule to solve a 3 by 3 system. Okay? And then in my next video, I'm going to give you an example and then give you a general formula to solve a system using Cramer's rule, even if you have more than 3 by 3, say n by n. Okay? So let's begin. So you have a system of 3 equations in 3 unknowns. The unknowns are x1, x2, x3, and you have 3 equations here. And as we talked about several times before, a linear system is same as a matrix equation is same as a linear combination, a vector equation. So the matrix equation here is the coefficient matrix. That's why I wrote these things, the coefficients of the system in a matrix format. So the first row is A11, A12, A13. Remember, in the first row, the first subscript is 1 and the second subscript tells you the column it is in. A21, A22, A23, A31, A32, A33. That's your coefficient matrix, and your variable vector is x1, x2, x3 unknowns, and you have output is b1, b2, b3. Okay? So this is your matrix equation. If you want, you could also write this as ax equals b, where this is your matrix A. Now I want to quickly review how you could apply Cramer's rule. I talked about this in the last class, but I want to review this. You could apply Cramer's rule as long as the determinant of this coefficient matrix is non-zero. In other words, this coefficient matrix should be invertible. So if this is invertible, we already have a way to compute this. You simply shift the inverse to the other side, you could solve the system. That's what we called inverse method. But this is a little bit different than the inverse method. It gives you exactly what those variables, what those unknowns are by computing some determinants. Okay? So let's see what we can do here. So the condition is that A should be non-zero. So you take this 3 by 3 matrix and compute the determinant. If the determinant is non-zero, then we can apply Cramer's rule. Then only, if the determinant is non-zero, then only we can apply Cramer's rule. Cramer's rule. Now let's say I want to compute the value of x1. And the process is similar for x2 and x3. So let's consider the following equation. I want to take A. A has 3 columns. This is the matrix A. Times, look at this matrix. I'm going to specify the columns of the matrix. So this is a 3 by 3 matrix. I'm going to write down a 3 by 3 matrix by specifying each column. I should have 3 columns. And each column should have 3 entries. The first column is x, x1, x2, x3, you call this as x. So the first column will have all these 3 entries. Maybe I could write it down here. x1, x2, x3. This is to compute x1, to compute x1. So in the first column, I write the variable vector. And in the second column, I write 0, 1, 0. In the third column, I write 0, 0, 1. Okay. In other words, I take the identity matrix here and replace the first column by the variable vector if you're trying to compute x1. Let me repeat that. In the identity matrix, you're replacing the first column, that is 1, 0, 0, by the variable vector. And I want to know what the product of these two is. So really, this is a 3 by 3 matrix. So if you multiply these two matrices, I should get a 3 by 3 matrix. Is that right? Yes. This is 3 by 3, that is 3 by 3, so the product should be 3 by 3. I want to know what the first column here is. So to compute the first column, you got to take the first row here, multiply by the first column. The first row is A11, A12, A13, and multiply by the first column will give you exactly the left-hand side. That would be the entry, which is equal to B1. So the first entry would be B1. What's the second entry here? First column, second row. You got to take the second row here, column there. If you multiply those, you get the left-hand side of this. That's your second entry here, which is same as B2. Likewise, the third entry is B3. Okay? Now, if I multiply to get the second column, I'm going to take this matrix and multiply by 0, 1, 0. If I take the first row and multiply by 0, 1, 0, only product that survives is A12 times 1. The second entry survives because this is 0, that is 0, A11 times 0, A13 times 0, they both go away. Only the second entry prevails. So this is A12. Likewise, this is A22. Likewise, this is A32. Now if you multiply A by 0, 0, 1, it works exactly the same way. This would be A13, A23, A33. So I want you to understand this. This is the very important point in this process. So when I take this matrix A and multiply by this matrix, I get the matrix here. And how do I construct this? The right-hand side matrix. Keep in mind, I'm trying to compute the first variable. So in the matrix A, you replace the first column by the output. That's the product here. Remember that. Now I want to compute the determinants on both sides. I want to compute the determinant of this product equals determinant of the matrix on the right side. These two should be same because they're same matrices. Now we talked about in the class, determinant of A times B is same as det A times det B. So this is determinant of A times determinant of this matrix here. Equals determinant of the right-hand side matrix. Okay? We're almost done. So you compute the determinant of the matrix, we know it's non-zero. Now I want to know what the determinant of this matrix is. If you look at it carefully, this is really a lower diagonal matrix. All the entries above are 0. Therefore, determinant of this is the product along the main diagonal, which is x1 times 1 times 1. So really this determinant is x1 times det A equals determinant of B1, A12, A13, B2, A22, A23, B3, A32, A33. So if you want to solve for x1, you simply move the determinant to the other side. So that means x1 is this divided by that A. Okay, let's look at that for a minute. So to compute the first variable, you have determinant in the bottom. You have determinant in the bottom. In the top, you're computing the determinant of a matrix, a specific matrix. How did we get that specific matrix? You take the matrix A and replace the first column by the output. Okay? Let me repeat that. In the top, for the first variable, you replace the first column by B1, B2, B3, that's the output matrix, and keep the remaining two columns and divide by that A. That's it. That's the formula for x1. So if I want to write down the formula for x2, it would be determinant of the matrix obtained by replacing the second column by the output, second column of A by the output. So you have B1, B2, B3, that's the second column. First column stays as it is, and the third column stays as it is. And divide by delta A. That's x2. Likewise, x3 will be simply replace in the matrix A the third column by B1, B2, B3. That gives you a formula to compute the determinant, to compute x1, x2, x3. And this process is known as Cramer's rule. Okay. I have a problem on the practice sheet I posted on the blackboard. One of the last problems is using Cramer's rule. So you just have to compute, if you have a 3x3 system, you compute 4 determinants. One, that A, one determinant of the matrix, replacing first column by these output entries. Another one, determinant of A, except replacing second column by the output, and the third column by the output. Those 4 matrices, 4 determinants will give you the values of x1, x2, x3. Hope you understood this, and I want you to solve that problem in the practice problem section. Okay, thank you.